except okay, so I may have to switch to, I'm going to switch to PDF. I apologize.
Okay, no problem.
And now it's good. Okay, so I'd like to thank the organizers for the invitation to speak here today. Appreciate it. So this talk is based on a sequence of works, in part with my collaborator Freddie Cacciazzo and several others. And this talk is, I would say it's a physics-inspired direction that we took that we'll take a look at. So these are the references, and so the motivation. Well, let's say what's the plan for today? Motivation for the talk comes from particle physics. In particular, there's a formula in particle physics called the Cacciazzo-Yuan scattering formula. It allows you to compute certain quantities in physics called scattering amplitudes. And out of this, out of the study of this formalism came the generalized associahedra, which I'm going to discuss today. So I mean, it's going to build everything up in lattice. So the question is, the associahedron is going to be the base case k equals 2 in a certain sense. And we're going to start by taking the associahedron, which is a relatively, relative to what we have, it's a fairly large polytope. Facet inequalities are given by some, I mean, if we take it to be integers, the standard realization, it's fairly large. They're given by some binomials. We're going to take the smallest polytope possible, thinnest polytope possible in the integer lattice, and look at the properties of that and then generalize that. So yeah, and then inspired by that, we'll look at a kind of k-ary generalization of this polytope, which we call the pk polytope, characterize facet inequalities. The next question is, the pk polytope, unlike the associahedron, is not a simple polytope, which means that the number of edges incident to a vertex is bigger than the dimension. But luckily, there is a deformation, which is a nice property to have in physics. You like to have polytopes that are simple. It's just a very desirable property that you want to have. And so that was finding a simple polytope with the same set of fixed facet directions was an important problem. And then from that, there were other connections to physics. And for experts, perhaps you recognize there is an interesting work on Grassmann associahedra in non-crossing combinatorics. And so we have a connection, unexpected connection to that. Dual polytopes, and at the very end, time permitting, I have a couple slides on a different generalization of the associahedron, which is connected to tropical geometry, tropical Grassmannians, and things. And so that's more recent work. We'll see if we have time. Are there any questions about the plan before we keep moving? Okay, so everybody knows, I think it's safe to say that most people know, everybody knows the associahedron if we draw it as a graph, which was how it was due to Stashev. It was later given a metric realization, but originally it was a graph that came out of some algebraic theory. Now, maybe you've seen it this way. If you take pairs of integers, you can build a certain complex whose vertices are collections of pairs, and where two vertices are connected if they share all but one of the elements in the collection. So that gives us another way. Notice that all of these guys, they have a certain, each collection is characterized by a certain non-crossing property. And I don't know if you can see that. Let me zoom in. 1, 3, and 2, 4 are separated by a simple flip relation. Now, what perhaps you've not seen is an associahedron that has a different kind of decoration on the vertices. Rational numbers. So what we do here, SIJs are in physics known as kinematic invariants. They encode the momenta of some particles in a given scattering process. So they're just numbers, though. A priori, at the end of the day, they are just numbers. And so what we do is we would assign to each vertex a product, the reciprocal of a product of these linear functions in the kinematic invariants. Okay, these are called Mandelstam invariants by the physicists. So the notation here is that if we have an n-tuple of integers, then we sum over all pairs in that set. So that's the notation. And then the amplitude itself in this particular scattering process is the sum of all of the integer weights, of all of the weights on the vertices. So these are examples of physical quantities, physical observables called scattering amplitudes. And this is what they actually look like. Okay, so you can imagine you have a scattering process and you got a number. Depending on the kinematic data, you may explore the boundaries and you'll start to encounter these singularities, the S12, S123. And if you degenerate, if you degenerate the scattering process such that you land on, if a certain sum of particles, certain subset of particles goes, quote, on shell, then the corresponding S ABC is 0, and you sort of explore this function. Now it's sort of a blob, though, right? You don't actually see this function. This gives us one sort of standard representation of it. I mean, a priori, this thing is just all you see is everything over a common denominator. You see some huge numerator. You don't know, and you don't know which singularities can be achieved simultaneously. But this is, Feynman gave us the Feynman rules, which give a sort of canonical expansion for the amplitude, for the scattering amplitudes. And so that's what this combinatorial mechanism does. So this is due to Feynman. We can attach these fractions, these simple fractions, to the vertices of an associahedron and take the sum, and that's equivalent to the formula that the physicists would write down, which is the following. I mean, and they would say that we are summing over the set of all trivalent trees with a given set of boundary labels on the leaves. And so as you vary over all trees, you get Catalan many summands. Notice there are 2, 5, 14 there. Yeah, and that's the, and so it's associated to each tree or Feynman diagram, you get you apply the Feynman rules, so you take the product of the reciprocals of the weights on the interior edges, and that's how you get an amplitude. So note here that if you set, I mean, this is kind of a trivial observation, it seems. If you set each kinematic invariant to 1, you get the Catalan number itself, right? But that's not entirely obvious that you can do that, because a priori, these are not independent. I mean, from a physical point of view, these do not have a, you don't have 5 degrees of freedom. You may have something less than that. Generally, you do have less. But in our situation, yes, we can do it, and that's the jump off point for the PK polytope, which I'm talking about. The PK polytope will arise when we set all of the kinematic invariants, the planar kinematic invariants, to 1. Yeah, so we'll take a quick diversion. How do physicists calculate scattering amplitudes in practice? And how do the Catalan numbers appear in that context? Well, CHY in 2013, 2014, they introduced a formalism based on a system of n rational equations called the scattering equations. Yeah, they're functions on the n-punctured Riemann sphere. And I write here delta ij for the difference sigma I minus sigma j. Okay, so here we're writing representatives. We're writing in the Riemann sphere, we're taking a chart, and we're writing the representative sigma I minus sigma 1 up to sigma n for the n punctures, taking a chart. And here are the 2 by 2 determinants come in and are the arguments of the logs. So the scattering potential is this. The kinematic data is assigned to as the coefficient of the log of the difference of the differences of the punctures. Hey, it is. And the miracle was that by performing some operation on this function, plugging it into an integral, what you get out is a number, and this number coincides with the value you get by placing the kinematic invariance on the vertices of the associahedron and taking the sum. So there's this beautiful, absolutely beautiful coincidence there. The scattering equations, you have to solve for the critical points of this function. And if you take the derivative in sigma I, or sigma 1 up to sigma n, you get n equations. Now, CHY Kachazov-Yuan showed that when your kinematic data Sij, when the Mandelstam invariants are generic, real, generic complex numbers even, then the system of equations not only has finitely many solutions, it has n minus 3 factorial solutions. And so, yeah, suppose now we want to, I mean, the rest of the procedure, the heart of the CHY formalism is the following. We solve and get these n minus 3 factorial solutions, and then we integrate a discrete integral. I mean, it's a sum over n minus 3 factorial terms, all n minus 3 factorial solutions, and we have to take the sum of this special integrand. This is called a Park-Taylor factor. We take a sum of consecutive differences of the punctures, take the square, and we have this coefficient weight. Now this is where the magic happens. Det prime phi. Det prime phi is the Hessian determinant. It's a certain determinant of the scattering potential. So this is what so that the whole physical process passes through det prime phi. So when det prime phi blows up, that means that that means the kinematic data has run into a singularity, and that says that Mn, that tells us that we're near a pole of Mn. And those poles coincide when this particular integrand is chosen with the combinatorial formulas that we just explained. So then later, the general formula, which holds for more fancy, even more interesting integrands than this, was proved by physicists Louise Dolan and Peter Goddard back in 2014 or so. So there, on each side, on the left side, there was a combinatorial formula for different scattering processes. And on the right side, you had some modifications of this by inserting some Pfaffian or other various things in the numerator, and that somehow tweaks the formula just right until you end up with a physical scattering amplitude. Yeah. So I'm going to move back into the combinatorial realm now, go back to PK polytopes. But this I really want to emphasize that there is this rich physical background that really informs this, and which was essential to the discovery of these polytopes. So remember, if we set all planar kinematic invariants, all kinematic invariants S, A, B, C, D to 1, we get the Catalan number. Right? We just saw that up above. Now remember, these S, A, B, C, Ds are actually sums of Mandelstam invariants, Sij. So you can either set all of these to 1, or you can set adjacent guys to 1 and Sii plus 2 to -1, and all others to 0. That's an equivalent. That's an equivalent statement. If you do that and evaluate the PK potential function, well, you're left with exactly a log of this very simple rational function, which we call the PK potential. Now, if you differentiate this, the scattering equations become very nice and simple. Everything is for a term, and you can solve it explicitly. The number of critical points drops drastically from n-3 factorial to this thing with just integer growth. So when n equals 5, you have 2 critical points, 2 critical points when n equals 6. So it's a highly combinatorial formula when this is the case. So CHY, they noticed that at the PK point, they showed not from the combinatorial formula, but by solving the scattering equations directly and plugging it into their formula for m sub n using the scattering equations, that it evaluates to some signed Catalan numbers. Now this was this involves a nice bit of combinatorics. I won't go into the details because we want to kind of stay focused on polytopes, polyhedra, but move back toward the associahedra. But there is this beautiful story here with the scattering equations, solving them at the PK point, at this PK point. And just the critical point, the distribution of critical points has a very nice interpretation. But yes, let us circle back to associahedra. Okay, so I'm going to fix a certain parameterization of the 2 by n matrices of the Grassmannian, in fact. So take all 2 by n matrices where you act by GL2 on the left. That's the Grassmannian. We're going to take this special map, take x1 up to xn, xy up to xn, and map it in this way. If you do this, then every 2 by 2 determinant becomes a sum of x's with some y coefficient. So it's just everything is just a very simple positive polynomial, right? And so what happens is if you take this to be a 2 by n matrix, take the product of all of the 2 by 2 minors, what you're left with is, well, it's a nice polynomial. It has some degree n minus 2 choose 2 or something. Note some of these will be 1, but you can take the Newton polytope of that polynomial. And so that's what that Newton polytope in the generic situation is the associahedron. But in this case, let's consider the following situation. We have only the labels involved in the pK potential. That is 1, 3, 2, 4, 3, 5, up to n2. And in the bottom, we have the consecutive minors. So if we do that, we'd like to find what is the Newton polytope for this. So we, if you look here, if you take every other guy, well, you're left with n minus 3 intervals, line segments, and 1 simplex. Right? N minus 3 intervals and 1 simplex. And we'd like to understand this polytope. We call this polytope the PK polytope. Now this is remarkably simple, but it also is has some rich properties. So some notation. Take a linear function gamma ij to be the following sum of alphas. Alphas are coordinates on r to the n minus 3. R to the n minus 2, I apologize. They are coordinates on r to the n minus 2. So we illustrate here what happens in n equals 5. The PK polytope here is x1 plus x2 times x2 plus x3 times x1, 2, 3. Well, maybe you'll recognize this as a pentagon. It is just a pentagon, right? And it's literally the metrization of the associahedron that was due to Lode. So that's dead on this polytope, and that's dead on the associahedron. So for n equals 5, the PK polytope is the same as the associahedron. Maybe I should pause for 1 second to see if everybody's happy here, if they have any questions or comments. Okay. Okay, so if we take this, right, we take the Newton polytope, right? And what you do is you expand this, read off the exponents, take the convex hull of the set of exponents, and you get this polytope. Now, this polytope is cut out by some inequalities in the alphas, in the exponent space. These, and they have this interesting form. Linear function plus 1 bigger than 0. Now, okay, well that's kind of nice. Let's see, let's move on to n equals 6. You recognize here 1, 2, 2, 3, 3, 4, 1, 2, 3, 4. Let me remind that the associahedron for n equals 6, it has 14 vertices and 9 facets. So the 9 is the Catalan number, the 14 is the Catalan number for n equals 6, and the 9 is the binomial. So 6 choose 2 minus 6. So that's the number of facets. So what we notice here is that the PK polytope still has 9 facets, right? But somehow some of the vertices have scrunched together. In fact, these two vertices are no longer simple. They both have valence 4. So each of those two vertices is special. It has valence 4. But the important thing is it still has the same number of facets. And in fact, in general, we can skip to the general formula. If you take the pK polytope, take these consecutive n minus 2, n minus 3 intervals and 1 simplex, then that polytope is cut out by this remarkably simple expression. Gamma ij plus 1 is bigger than 0. And that's it. The associahedron would involve a binomial here. Gamma ij plus some j minus I plus 1 over choose 2 or something. But this is very simple. And the same set of facet normals, the same number, exactly the same number. So that's kind of cool. Yeah, so this story is about G2n. So now maybe, we wrote down, we have this parameterization here for G2n. Maybe there could be one for GKN. And maybe it could have the property that we have this very nice tight structure on the facets. That's not such a, if you know about just from the Grassmannian, that's not really to be expected. I mean, the Grassmannian GKN is even G3n, it's a very complex beast. But to somehow we'll be able to find a nice simple polytope from it. So here, k equals 3, we can do the same recipe. We can take the Grassmannian G3n, and this was discovered by my collaborators, and back in 2019 or so, we introduced this Cacciazzo, Guevara, Misera. We introduced this, and what happens is you do the exact same procedure, taking 3 by 3 determinants, on G3n, again, have these so-called Mandel-Stem invariants, except now they have this different property. You have a repeated index at 0, and you have, again, these n constraints. Okay, so you can play the same game. You can ask, what are the critical points of this function, where you take derivatives on G3n, or more precisely on its torus quotient, but we can think G3n. You take the critical points. You can do that game. Let's jump directly to the special pK point. So we set all cyclically consecutive guys to 1, and then when you have this jump, I plus 1, I plus 3, you set that to -1. Well, then this function simplifies to this remarkably simple expression here. And what are we going to do? We're going to build a polytope from this. And we'll jump directly to the all kn definition, and then return to the case k equals 3. So if you do this game for any k bigger than or equal to 3, well, you get a bunch of simplices. Those are obviously simplices, and they're of dimension n minus k minus 1. Just a homogeneous polynomial, just the sum of the variables. So you get k minus 1 of them. I goes from 1 to k. But then you also get these are not obviously simplices, but they are simplices. They're of dimension k minus 1. They're of dimension k minus 1, and you get like n minus k of them, n minus k minus 1 of them. And that's it. The pK polytope for arbitrary k is a sum, Minkowski sum k minus 1 simplices of dimension n minus k minus 1, n minus k minus 1 simplices of dimension k minus 1. Okay, pretty simple to state. Pretty remarkable is what actually happens to the facets, the facet normals, to the dual polytope, and to the face lattice of the thing. So observation 1, it has n choose k minus n facet inequalities. Remember, the associahedron had n choose 2 minus n facets. This PK polytope also, it has n choose k minus n facets. That should be an indication. Well, this is kind of curious. It is not a simple polytope. Immediately, you see that immediately. Now you take the PK polytope and you interchange the roles of the vertices and the facets. So the PK polytope for k equals 2 has gamma ij plus 1 bigger than 0. Build a new polytope with vertices, the gamma ij's, and calculate its volume. That's what's the interesting thing is. So I'll explain that carefully. The volume, the statement is, the volume of the polar dual polytope to the PK polytope is the Catalan number, the k-dimensional Catalan number, which is the number of standard Young tableau of shape k by n. Okay, just like this is also when k equals 2, this is just the Catalan number, just the usual Catalan number, 2, 5, 14. That's the volume of the dual to the associahedron. So the dual to the associahedron is a well-known, much-studied object connected to the AN root lattice. Comes up in cluster algebras. Okay, so let's look in smallish cases what happens. Here's our parameterization for k equals 3 and n equals 6. Okay, it is what it is. It's not particularly important what the polynomials here. What matters is that the 3 by 3 determinants are always polynomials with positive coefficients. In particular, coefficients are 1. And the Newton polytope we take here, we take the Newton polytope with these products. So 2 triangles, 2 simple triangles, and 2 sort of transverse triangles. Okay, this is a 4-dimensional polytope. Notice the degree in x, the degree in x1j, the total degree is 0. The total degree in x2j is 0. I don't know if you can see that. Just take a second to convince yourself. That means that this polytope contains the origin in its center. So we take R3 cross R3, 3 guys, x1, x11, x12, x2, 13, etc. And it contains the origin in this Cartesian product space. Okay, so let's we're going to try to understand the facet normals to this object, which I think is kind of cool. So by analogy, remember the associahedron has facet normals. Just block out, just take the first guy. That looks like it would be the facet that would encode a facet normal to the associahedron, but we're going to pair it with another one. Right, so alpha 1t plus alpha 2t, and they're summed in this kind of staircase. We'll see that in a second. Okay, we introduced that, but just I want to sort of just for a moment, if you'll indulge me for a second, I want to show the actual procedure of how how one might discover this, and then we'll go into technical details. So you take this Newton polytope and you plug it into Sage, right? And out you get what you get are these very nice, simple inequalities. They're all 1s and 0s. This -1, you stare at it for a minute. Well, that's actually That's actually not. It's actually a 1, 1, 0 because you have a 1, 1, 1 up here. So everything is a 1, 1, 0 vector. All the normals are 1, 0 vectors. And you try this for like n equals 7, n equals 8. Well, then you can start to make a conjecture. And conjecture you arrive at is this formula. So when you see this row here, you should think this is actually a 2 by 3 matrix. So the alpha, alpha 1, alpha 2, alpha 3, alpha 2, 1, alpha 2, 2, alpha 2, 3. Okay, so that's kind of the underlying. This whole thing has a physics sort of a physics guided sort of experimental approach that I then tried to make mathematically rigorous and got this new result about the volume. Yep. So here is this gamma ijk. These will hopefully play the role of the facet normals, and we're able to show that they do. So now look at this. This is kind of remarkable. The facet inequalities, we can conjecture and then prove again by this very simple formula. Just gamma ijk plus 1 is bigger than or equal to 0, and that's it. If you know a little bit from other areas of convex geometry, maybe a little bit of mirror symmetry, you might recognize this expression. This indicates, this particular expression suggests that it's a reflexive polytope. It's so I'll just throw that out there. Maybe an expert will recognize that. But this family of polytopes that are defined by inequalities of this form. They can be important in some areas. So just very quickly, some examples. What is it? What do they look like? Well, we can represent them on a grid, and like so. So the first time you have something that involves 2 rows is gamma 1, 3, 5, when the steps are in size at least 1. So then you have a gamma ijk where both step sizes are size at least 1. Then you'll involve both rows, and that's what it looks like. Maybe I should pause again just for a couple seconds. So we'll go with the general definition for the PK polytope for the normal vectors. Okay, so it's given by this staircase. You draw a k minus 1 times n minus k minus 1 grid. You take all downright paths like this. Wherever you have a node, you put an alpha ij in the corresponding sum. So this is alpha 2, 2 plus alpha 2, 3 goes here. And then note that 6 and 7 are adjacent, so you skip a row. Then you get 3 in a row. And then 13 and 14 are adjacent, so the last row is missed too. Not extremely important, but there is this sort of very suggestive grid representation, which in fact is useful if you want to prove general properties about these objects. And, so I might mention something about that at the end, or later on. Okay, so among these, once you have this definition of the gamma ABCs, or gamma capital J's, you start to say, what sort of linear relations do they satisfy? Well, they're very simple. There are all these sort of interchangings of crossings and nestings. So let us consider like a totally interlaced pair, 1, 3, 5 and 2, 4, 6. Well, it turns out there are 4 different ways to express this different linear combination. And one of these ways is particularly significant. Yeah, so these 4 different ways come by flipping the roles of the corresponding indices. Like you switch 5 and 6 in these here, switch 3 and 4, switch 1 and 2, etc. So that encodes all of the information here. Now this one, I just want you to remember 1, 4, 5, and 2, 3, 6. The pattern here is important. In fact, when you take the deformation which we want to a simple polytope, this is going to encode the face lattice of it entirely. So this bottom guy is the most important one. That will be considered non-crossing in our sense. So the theorem was that if you take this definition for the gamma j's, then the Newton polytope, the PK polytope, is cut out by these simple inequalities. Gamma j plus 1 bigger than 0. Yeah, so I mean, there's 2 things to prove. And to prove that, you get all facets. I mean, there's facet define everything. You have facet, everything is facet defining. So the PK polytope is contained in this thing, then you have to show that everything is facet. So it's a little bit technical, but it is cool, and we'll just show you the technique when k equals 2, the technique for finding facets here. We can move a little bit faster, I guess, but so here's the idea. You take a linear function like gamma ij, gamma ijk, it's some hyperplane. And we have a polytope here. We have a hyperplane, and as we slide this hyperplane toward the polytope, it's gonna bump into the polytope at some place. You slide it too far, it's going to intersect the interior. But there is a unique position where the linear function that defines that hyperplane is minimum. It achieves its minimum on some face, and a unique face of that polytope. So that's the method of proof. You take a linear function here, slide it around until it achieves its minimum value on the polytope, and then you calculate what you calculate the dimension of that face. So that was the idea. You take one of these gamma j linear functions and then calculate the dimension of the face where it's minimized, and then you show that as dimension 1. That's a codimension 1. Yeah, that's the idea. So you take gamma 2, 5, alpha 2 plus alpha 3, evaluate it on each of these linear functions, and then you get a square. The Newton polytope is for the face where this is minimized is just a square. It's the product of 2 intervals, x2 plus x3, x1 plus x4. So that says that indeed gamma 2, 5 does characterize a facet, right? Because this is a 3-dimensional polytope. We've shown that it's minimized on a 2-dimensional face. So it's that is indeed a facet, and the value is -1. So that confirms our formula. Now, of course, it's more complicated in general because you have these sort of transfers. Remember, I had p polynomials and q polynomials. The p's were very simple sums of x's. The q's were higher degree homogeneous polynomials. There are a bunch of them. But that's basically the idea. Okay, so let's notice that the PK polytope is not simple. In the case k equals 2, there's an obvious sort of fix, which is to take, we know what the facets, the deformation parameter should be, and we deform it and we get the usual associahedron. So can we deform it to a simple polytope? That's the next question. So we're going to take a little bit of another, if you'll indulge me, we're going to take a physical digression and then take the deformation. So this is another cool construction, which sort of takes a polytope and replaces it with what a curvy object. It's a curvy associahedron. I mean, it's defined by some binomial equations, and it takes up, it's sort of a curvy region, which in a cube, which still has the same face lattice as the associahedron. Maybe I'll skip down here. Well, but before this, let me ask, just pause again for questions or complaints or anything, or questions or comments. It's good.
Can I ask a question?
Yeah.
How Feynman diagrams are connected to the associahedron?
I'm sorry, say again, please.
How do Feynman diagrams? How Feynman diagrams are connected to the associahedron?
So in a word, yes, the Feynman diagrams are combinatorially trivalent trees, which are dual to triangulations of a polygon. Triangulations of a polygon, from that you can construct metrically the associahedron itself. So Feynman diagrams correspond quite precisely to the vertices of the associahedron.
And we don't consider loops in the diagrams.
Say again?
Do we consider loops?
No, this is only, oh, thank you for the question. No, this is only tree level. Yeah, no loops. Yeah. Okay, so I guess I'll continue. We take the 2n Grassmannian again, and we'll define some functions on it, some cross ratios that are independent, that are invariant, that are preserved, that are constant under the scalings by the column on each column. So it's independent of column scaling. So here it is, these special planar cross ratios. Uij equals Pij, Pi plus 1, J plus 1, like this. Okay, so you have these guys. Notice that there are exactly n choose 2 minus n of them. It's not defined when j equals I plus 1. So you have n choose 2 minus n of them, which looks the same number, of course, as the number of facets of the associahedron. And it's not an accident. In the case when k equals 2 and n equals 4, well, here u13 and u24, they have the nice property that they sum to 1. Well, that's nice. But if you go to n equals 5, they have this remarkable binomial structure, a binary structure. If you take a uij and add to it the product of all ukls that cross 1, 3, so 2, 4 crosses, 2, 5 crosses, we come over here, u13, u24, and u25 cross that diagonal. So u13 plus the product of all uijs that cross it, and you get 1. So that's a general sort of formula. It was that you can take to be the defining equations for some curvy object. I mean, it's not obvious that it even has a solution, but we just found that we just know by construction that it does. What I mean is you could take these to be just the defining equations on an abstract object, right? Does it have a, is it consistent? Does it have a non-empty solution set? We've just proved that it does by the explicit parameterization. Okay, so we can define this inspired by physics. We'll define this so-called world sheet associahedron to be just the solution space to these set of equations. And yeah, not obvious that it's not empty, but it is. So, okay, well, that is a tunus to it. Can we do the same thing for our higher KPK polytopes? Is there an analog of this formula for the polytopes we were discussing before, the PK polytopes pi kn? This will correspond to the desired deformation of the PK polytope that will be a simple polytope. Okay, how do I get this out of the way? Okay, so we would like to introduce a k=3 generalized world sheet associahedron. Well, the important the property that it turns out is significant here was introduced, appeared in Santos, Stump, and Welker. It first appeared in work of Pavliovsky, and it's the following. It's a lot of text, but let me just say in words what it does. If you take a triple, you have to check 3 conditions to see if it's crossing or not. You have to check adjacent pairs. So the first two, the second two, and the first and the third. If the first two are crossing, if the second two are crossing, then you're bad. The pairs 1 and 3, that can be crossing if the interior guy is not the same. I mean, if I2 does not equal J2, if I2 is not equal to J2, then you can still have a non-crossing pair. Okay, maybe that's a little. I mean, it's sort of a. What happens is that it was proved by Peterson, Pavlovsky, and Speyer. If you build a graph with edges, all the vertices of the graph are labeled by triples. And the edges of the graph are pairs of vertices which are non-crossing according to this rule. Then all maximal by inclusion collections of pairwise non-crossing triples has cardinality 2 times n minus 4. That's sort of a paraphrased, yeah, but that's the really important property here that we have. Okay, so let me zoom out. So here to illustrate the crossing condition, clearly 124 and 135 is crossing. 135, 236 is crossing. Notice that 3 is the same here and here, but 1, 5, and 2, 6 are crossing. Now here, 1, 5, and 2, 6 are crossing, but 3 and 4 are not the same. That means that this would be considered a non-crossing pair in this convention. So what we'll have is some system of equations like this, where this non-crossing condition, the obvious one here, is replaced by this condition here. And here it is. We take a 3-element subset. And then we have the following equality. We take the product over all ui's, the product over all i's that are crossing with j. But there's this trick here for higher k that you have no longer all unit powers. You have to take a power which is proportional to the number of times, well, equal to the number of times that the non-crossing condition is violated. So there it is. And here's a complete set of solutions for the 3-6 world sheet associahedron. So it's pretty beautiful. I mean, we have this Grassmannian G36, and we have this algebraic structure on it, which just perfectly encodes the, well, we will see that as a function on the Grassmannian. I haven't, oh, sorry, I'm in the middle of the talk. Thanks. So if you apply this rule, well, look, if u124 equals 0, then according to this rule, every time, whenever you have something, u, a, b, c that is crossing, that has to be 1. So u135 has u124 in it, etc. So from these equations, these equations encode the entire non-crossing complex. I mean, you can reconstruct the whole thing working backward if you want. So you might ask, once you have a polytope or a set of equations, what happens when you start imposing conditions? Let's impose one of the conditions, u124 equals 0. Well, you get a new set of equations, and this new set of equations characterizes a new curvy polytope. Now here I've labeled the vertices of this polytope with quadruples, with 4-element collections of triples. So here, 1, 2, 4, don't know if you can see that. 1, 2, 4 is in every single collection. So this is a facet. This looks like it should be a facet of some 4-dimensional polytope. And so these are the facets of a 4-dimensional polytope. You get a, yeah, that's what they are. You get a cube and an associahedron and something else. Is there a question? Somebody had a.
Yeah, so it's in the chat. What is the relation between W36 plus and the Newton polytope you constructed before?
Yeah, that's what we're coming to right now. So I'll say very quickly and then move to the detailed answer, which is the parameterization of W3n plus. It uses ratios of polynomials. Okay, so each u135 is going to be a ratio, a simple ratio of two polynomials. If you take the product of all of those polynomials that appear in all uijk's, the Newton polytope of that is it's the guy we want. It's the Newton polytope. It's the generalized associahedron. I think that was the question, right? Yeah. So that polytope generalizes the associahedron. In the case k equals 2, you parameterize the world sheet associahedron with some simple linear rational functions. Take the product of all of those polynomials that appear, and you get the associahedron itself. That's the general idea. And here is the explicit solution. What matters here, I don't want to torture you with the indices. What matters is that it's either degree 1 or degree 2. Right? You get these tau polynomials. Everything is just either degree 1 or degree 2, and that's it. There's nothing with higher degree. nothing of higher degree. And this miraculously satisfies those equations above. So here's the condition for the tau polynomials. When 1 is an index in the set, then it's just a linear polynomial. When 1 is not in the set, then it's a degree 2 polynomial. It has this kind of staircase condition. I mean, it basically says you take two intervals, and then they have to overlap by a single guy. You know, j minus 1, j minus 2. Right? They have like a unit overlap, and then you sum over all pairs, one in each interval, such that the bottom pair is at least to the right of the upper pair, the upper guy. And that's it. It's that simple. Here's the definition for k equals 4 and n equals 14, I guess. Maybe n equals 16 because I'm going up to here. So it's just a diagrammatic representation I came up with, but it turns out it actually does have some meaning in quiver representation theory. Yeah, and in fact, that the joint work with Hugh Thomas, we're using quiver representation theory to prove that the solutions actually, the U polynomials actually do, with the parameterization we've seen, that they actually do satisfy and characterize the world sheet associahedron, W3n, WKN in general. Yeah. So, okay, so here's the thing. There was a conjecture from 2021 that if you take the product of all of the tau polynomials, you get a simple polytope. Moreover, the face lattice of this polytope, say, is encoded by the non-crossing complex, according to that weird rule with pairs of indices that can be crossing if the interiors are not equal, whatever, right? So that was the conjecture, and we're proving it in using quiver representations. So if you're familiar with the work of, or curious about it, the work of Santos, Stump, and Welker, once this is a theorem, it will provide a Minkowski sum decomposition for their so-called Grassmann associahedron. So this was a polytope they had constructed abstractly, and so this provides a Minkowski sum realization of it. Okay, so PK polytope, 3/6 case. Here are the four polynomials. Well, we enlarge it, include all tau ijk's, and we get 10 polynomials. And that's it. It's a simple polytope, satisfies, I mean, again, plug it into Sage, satisfies all the nice stuff. But look at the F vectors. There's 42 vertices, 462 vertices for 3,7, 3,8, 6,006 vertices. Those are the three-dimensional Catalan numbers. Yeah, and notice that the number of facets is n choose 3 minus 3 again. Sorry, n choose 3 minus n. Okay, so we're going to switch gears now and ask about, we start with the PK polytope, which has now these simple defining equations, gamma j, where j is a capital set. It's a set plus 1 bigger than 0. Now we're going to take the polytope, which is the convex hull of the gamma j's in the dual space. Right? Well, that is a very nice fellow. By analogy with the case k equals 2, I call it the generalized root polytope. And here we impose, we take it to be in the sum zeros hyperplane, where each row in the parameterization sums to 0. So that means that you always have n choose k minus n vertices of this guy. Okay, well, you can plug it into Sage. Well, look at this, 7 divided by 4 times 4 factorial is 42. 42 what we expected. And you can get the volumes. So when you have such a nice volume formula, what can you do? You can triangulate it. Maybe it has a nice triangulation into simplices of equal volume. And that would be the ideal situation, and that's what happens. So here are the k-dimensional Catalan numbers, and here, just for reference, I mean, for concreteness, this is one of the simplices in R to the R superscript 4 subscript 4. This is a 9-dimensional polytope. Vertices form a non-crossing collection. I'm using it. Sorry, I'm using a different notation V here, but we can think gammas. So I mean, I realize this in the space itself, but it's. I mean, we can think of this in the dual space with alphas. It doesn't matter. Just notation. So theorem is that the generalized root polytope has relative volume, the k-dimensional Catalan number. Idea of the proof. If you're familiar with a result of Gelfand, Graev, Postnikov, it might not surprise. But this generalizes their result. It's like a k-ary generalization of the triangulation properties of the root polytope. So let me remind you, the root polytope is the convex hull of the origin together with all roots, ei minus ej for I less than j. Okay, so this root polytope R k n minus k is generalizes that, and we have a triangulation that generalizes the one they have into the Catalan many simplices. So in their setup, they use these alternating trees. Here, there's always there's a little subtlety here. In their setup, they always have an arc from the first to the last. That corresponds, I mean, physics would not see that arc. So that's like saying there's an overall whole to the whole amplitude that factors out. So that arc somehow, that overall arc is this red point here at the front vertex. Right, so when I impose the condition that when I impose this condition, that the sums of the alphas in each row 0, that identifies the front point with the origin. So we get a polytope of dimension k minus 1 times n minus k minus 1. So, but for good measure here, there's the non-crossing triangulation for the 2-5 root polytope into these 5 simplices. Or maybe I should pause for a second, or should we keep going? Keep going.
Are there any
Keep going,
questions?
keep going, no?
Okay.
Okay, cool. Okay, so okay, let's discuss a little bit about what the proof actually looks like, and it's interesting. Yeah, I mean the structure of the proof is interesting and informative, I think. So in 3.6, the 2-5 root polytope has 2 natural embeddings. And it's embedded as you can see here, where you take the set 1, 2, 3, 4, and what changes is where the gap is. So we have a gap on the left side, gap on the right side. those characterize the two embeddings. So alpha 134 is alpha 11. Alpha 145 is alpha 11 plus alpha 12. I'm not asking you to remember the formula, but take my word for it. This guy is alpha 125 is alpha 21 plus alpha 22. So this is alpha 1j and this is alpha 2j, these guys. 1j, 2j. All right, so we're gonna, in general, the idea is take a non-crossing collection in each row according to the k equals 2 structure, the usual k equals 2 structure. Then we're going to kind of combine them together, just throw them together into a bucket and just sort of filter out until we get a collection which is non-crossing in the new sense. So instead of k minus 1 instances of the k equals 2 non-crossing condition, we're going to sort of blow that up into a full blast k non-crossing condition. Okay, so we take a point. A, where A and B are some positive numbers. Notice that this is crossing. 134 and 235 are crossing. Do you see why? We have 3 in the middle and 1, 4, and 2, 5. That means it's crossing. So depending on which of A and B are bigger, then we can expand into a non-crossing collection. 135 and 235, or 135 and 134. So that's basically the idea. You pick a point in your ambient space, and then you just sort of, you inductively, you project onto the first k minus 2 rows. Inductive assumption says that's a non-crossing collection, and bring in the last row and apply this rule and argue lexicographically or something that terminates. Example 4.8. Then there are 3 natural embeddings. That should be a 3. Look again where the gap is. The only thing that changes is the missing element in 1, 2, 3, 4, 5. So theorem is, for any collection of non-frozen, a frozen subset J is a cyclically consecutive subset. It's like 1, 2, 3, 4, 2, 3, 4, 5. And if n equals 8, 1, 6, 7, 8 is cyclically consecutive. That's a frozen guy. 1, 2, 7, 8, 1, 2, 3, 8 are all frozen. So the set of simplices that are labeled by these non-crossing collections defines a flag unimodular triangulation of the generalized root polytope. So unimodular says they all have the same volume, 1, same relative volume, 1. Flag says that every face is labeled by a complete graph. So I recall this. So as a corollary to this enumeration of NCKN is the k-dimensional Catalan number, and the unimodularity, we have that the volume is the k-dimensional Catalan number. I'm going to talk just. Yeah, so yeah, so okay, we're approaching the end here. So let's go back to amplitudes for a minute. Okay, remember at the very beginning we had an associahedron whose vertices were weighted with these simple fractions. And then we can construct the fraction by taking the sum of all the weights. So that's our amplitude, right? Well, idea is the same. Let's generalize that story. Here are the amplitudes you get from this new polytope. Right, so we get a rational function. You also have a notion of scattering equations here. Remember, we had this alternate analytic formula where we sum over all of the critical points of the scattering potential. And you have this nice integrand with the det prime phi, the Hessian determinant in the denominator to control which tells you when this thing has singularities. But anyway, this says that this is a generalization of the tree level cubic scalar amplitude for a fixed planar order to some sort of 3-ary, k-ary, some k-ary generalization in which the amplitude can be expressed completely combinatorially using this non-crossing complex. So each one of these guys are in bijection with sort of generalized Feynman diagrams. So they're in bijection with the vertices of the PK associahedron. Now, I guess I'm holding off on calling it the Grassmannian associahedron or the Grassmann polytope until we get until it's actually a theorem. That's what it actually is. And maximal simplices in the generalized root polytope. Yeah, and I guess that's it. Thank you very much.
Let's thank the speaker for the talk. Are there any questions?
Thank you. I have some very vague general questions.
Sure.
Okay, so just I guess maybe going back closer to the beginning of your talk, like I guess there's this sort of general idea about like scattering amplitudes and stuff about like volumes of quote unquote polytopes, but maybe not. And if you think about their poles, you can also look at triangulation and polytopes and so on. Like, when do these things like actually come from polytopes? Because in general, like that's not really the case, right?
Sorry.
In general, I was thinking about in the context of amplitude, which are like not polytopes, but
I'm sorry. Did you say last thing?
I guess what I was asking was, when do scattering amplitudes come from actual like volumes of actual polytopes? Because I don't think this is generally true, right?
It's yeah. I mean, it's
like, do we know and have any idea like when that would make
no.
sense?
I mean, well, there are lots of cases. I guess. I mean, one would hope, I guess, as just on a matter of principle. I think the idea. I mean, I don't want to speak for physicists. I mean, but I think the idea is that to look for amplitudes which are encoded by not always polytopes, but in general some polytope-like object, like the amplituhedron.
Yeah, exactly.
Right. Yeah. So no, that's a great question. Like, is there a condition? And I mean,
Yeah, I was wondering if there's like some space. This is not a well-defined question, as you can see, but I was just kind of curious.
yeah, I mean, basically, yeah, an intrinsic characterization of all amplitudes, all scattering processes that can be encoded by polytopes. I think that's a great question.
Okay.
But I mean, like, I will say, probably tree level amplitudes. I mean, I don't think you can push it to higher loop level things. I mean, then you have all kinds of infinities.
No, oh no.
Yeah, right. But if you stick with tree level, I mean, I don't know. I think it's a pretty natural, and you have a good chance of finding a polytope if you take some scattering process and see what combinatorics encodes the singularities. You know, I think it's a good bet that there might be one.
All right, thanks.
Yeah.
Any more questions?
I have one question.
Mm-hmm.
How, when you define the Newton polytope in the beginning, how do you find the normal vector? of the facet?
How do we find the normal vectors?
You say you evaluate some function and find minimum value, and then
So yeah, and in practice, yes, in practice, there are algorithms to do this. I mean, this is a deep question in optimization theory. There are a lot of different algorithms to do this, but yeah, it's implemented in Sage. Of course, you know, general, yeah, but I mean, I guess Sage and Polymake have the best algorithms to do this. I think this is what you were getting. Or did you?
But if you, so you need to have those half plane, and then find a vector there, or
Oh no, I see. No, I mean, right. So I came with some candidate facets. So I'm guessing what facets might be there. I mean, so I have some linear function. I'm saying maybe this is a facet.
Yeah.
Maybe it's minimized on a facet. So I have to do an optimization problem to calculate where it is minimized, and then I have to check the dimension. Right. I mean, but a priori, I mean, given a polytope to find the facets, yeah, that's a quite difficult problem. Probably, I don't know the difficulty in the NP if you talk about that, but it's quite difficult. It grows exponentially for sure as you go to high dimension.
Yeah.
Yeah.
Thank
Thanks.
you.
Thanks.
More questions? If not, I'll stop the recording.